So if you thought that the stuff we'd been doing over the last couple of days was pretty kind of boring and like, this is grade 9 stuff, that kind of thing, well, our world is about to increase in size, our mathematical world, fairly drastically. Quick review. This is the scalar equation of a line in 2 space. Okay? And what is the normal to this line? Vector A, B. And therefore, a direction vector would be, this is just a review of what we talked about, negative BA. The really important thing, remember what I said, and this will become very clear today, is I think you want to remember, I mean, it's hard maybe if you're doing the practice not to memorize both. A lot of you are just going to be like, I know it's negative BA. I know that's a direction vector. But it's more important to me to remember that this is the normal. Again, you'll see why later. And to recognize that the dot product of these has to be 0 in that they are perpendicular to each other. That's what a normal is. If this is my line, a direction vector on that line would be like that. And it doesn't, direction vectors don't have to be on the line. They can be parallel, right? Same direction vector. The normal is perpendicular. By definition, that's what a normal is. The magnitude isn't important, except we, as a general rule, use the sort of smallest magnitude that we can, just because it's kind of like lowest terms of a fraction, that kind of thing. So generally speaking, we're going to reduce direction vectors and normal vectors when we can, because it's just easier. And then we all are working with the same numbers. Make sense? And I've already told you that there is no scalar equation of a line in 3 space. Why? Because take a look at this. This, ax plus by plus zz plus d equals 0, is the scalar equation of a plane in 3 space. What is a plane in 3 space? Strange. Well, you've been working with a 2-dimensional plane for a long time. The xy plane, the Cartesian xy axis that we use all the time, is a 2-dimensional plane. The difference is we're only working in that plane. What does it mean to work in 3 space? Well, we talked about how you could draw the x, y, and z and put points in different areas. And in fact, let me show this. So this looks like 2-dimensional space, but it's not. So if I want to plot a point, let me move one. Whoop. There we go. Now I've got 2 points. One of them is kind of in that gray lower plane, but one of them is out up in space. Yeah? So that's what 2-dimensional space means. But what is a plane? Well, that's a plane. So 3 space, just like 2 space has infinite lines that can go in all different angles and directions, 3 space also has lines. And they're not just like going across each other. They're doing all kinds of other things that we're going to get to. We're going to talk about how lines interact with each other in 3 space and that kind of thing. And it gets pretty complicated and pretty interesting, I think. But 3 space also has planes that can be defined just like lines with equations. And this is what they look like. But that plane goes off to infinity in every direction. Now, it only looks like a square because that's all the technology can do. But it goes off in all directions. One of the questions in one of the days of homework coming up says, check your answers with 3D technology. It's obviously optional. You can do it or not, but I would encourage you to do so. And this would be a good tool to use, GeoGebra, because it has this 3D graphing ability. And in fact, there's a pretty good version for both iPhone and Android that you can use. And the last time I looked, there's a really cool version, but it was iPhone only, and I'm not sure why, just because GeoGebra is made for free by people volunteering their time, so nobody's got around to the Android version yet. But it's like a augmented reality version, so you can take 3D things and like put them on a table and look at it through your phone, kind of thing. So if you have an iPhone, you could try that. It'd be interesting to take a look at that. We could do that at lunch sometime, or if we have time in class. And you can inspect 3D things pretty interestingly. So anyway, something worth trying. But you can also just graph in the online version or the desktop version or whatever. It's available for Chrome and phones and everything. And sort of think about this stuff. Visualizing this, I think, will be important. I mean, you've spent a long time visualizing lines and two-space, visualizing three-space and thinking about its properties and that kind of thing. And planes in particular, I think, will be helpful for your success moving forward. Anyway, there's a plane. So that's what it looks like. And it's defined this way. So let's draw that. Whoops. So here's my plane. For some reason, we often refer to planes. I don't know how wide a convention this is used. I have often seen planes referred to as P, like lines are referred to as L, but we like to use pi here. So this is plane pi. What do you think the normal to a plane in three spaces? Wild guess, anybody? Very good. ABC. This is why I think it's useful and easy to remember what the normal of a plane is, what the normal of a line is, and then use that to find direction vectors as needed. Turns out the normal is one of the most useful and important kind of defining properties of a plane, because there's an infinite number of direction vectors that are parallel to that plane. There's only one direction vector scalar multiples of it that are parallel to a line, but a plane can have direction vectors all over the place, right? So I could draw vectors all throughout but it only has one normal, or scalar multiples of that. I can move that normal around wherever I want. It's always going to be perpendicular to that plane. So it's a useful way of defining the plane, and it's also just useful in terms of the notation and the things that we do. And I'm just going to make a note of this because it's really important. There's no scalar equation of a line in three space. Why not? Why can't they make one? Because the scalar equation is of a plane. It just is. It is that of a plane. So you can't also have one of a line. This is really important to note. There are a few questions that will pop up that will, in a way, try to trick you, or just the way they're worded, and the question doesn't make sense, or you have to be careful of how you're answering it because of this fact, that there is no scalar equation of a line in three space. So be aware of that, be careful of that. The other thing that you want to know is, and this will be apparent throughout what we do, is that identifying the equation of a line versus a plane is very straightforward, but it's something you need to be able to do easily. There is usually one or two people who get to the quiz or the test and they mistake a line for a plane, and that's a big, silly, bad mistake, and it's like, oh my gosh, I mean, what a waste of time. Like, We can't do anything if we can't tell the difference between these two things. Okay, so it's obvious, but we'll point it out explicitly, and I want you to think about it to make sure you get it. That's all. Okay. This definition of a plane for us isn't going to be a big deal, but if you went forward with this like anything, it would become a big deal. What's the difference between something that's a plane and not a plane? And if you went into like higher level theoretical mathematics, there are all kinds of big areas of mathematics that study this kind of thing, but we're not going to get into that. Okay, but the definition technically of a plane is a surface such that any straight line connecting any 2 points that are in the plane, any 2 points, the line connecting them lies entirely in the surface of the plane, entirely in the plane. What does this mean? It means I can draw any 2 points in that plane. We'll call them P and Q. Any 2 points. The line connecting them is entirely in the plane. So what would be something that's not a plane then? Well, bear with me. I'm going to try to draw one. Something like this. I think that's all right. I was practicing this before, but Seema interrupted me, so that's the best I'm going to be able to do. And so I could draw 2 points in this, whatever it is. And when I draw a line connecting them, it leaves the surface of that thing. So that thing is not a plane. We're not going to look at these things. And so knowing this fact is not really going to help you. But anyway. In this course, I mean. It's interesting when you think about like theoretical physics, and we now know that things like black holes, in fact, anything, warps space, but a black hole warps space a lot. Space is like a curved surface around objects that have mass. And the definition of a line is the shortest distance connecting 2 points, which means in space sometimes the shortest distance connecting 2 points is curved. And it's almost like seems contradictory that a straight line is the shortest distance between 2 points, but in actual space it can be curved, would be the straight line. So anyway, I'm not going to get into this too much, but it's kind of interesting. And you can see how extending this thinking to planes would have the same sort of, I guess, step up, and the difference between doing it mathematically and doing it in real life sometimes. Definitions are different. Anyway, any questions so far? Okay, this can be important to uniquely define a plane. There's actually more than what we're going to look at. We're going to look at 2 because, again, mathematically with the notation we use and the things that we're going to do, we only need these 2. But technically speaking, if you're reading about this, there are other ways that you can define a plane uniquely. But one of the ways would be with 3 points in the plane. As long as these 3 points are not collinear, which means in a line with each other. This idea becomes very important moving forward. whether things are collinear or not. I mean, think about it. If you had 3 points that were in a line, you could take a plane and kind of swivel it around those 3 points, right? Doesn't that make sense? But if you have 3 points that I would picture it as forming a triangle, so 1 point here, 1 point here, 1 point up here, all of a sudden you've got a plane that exists in a particular position in 3 space. We also call this linearly independent. So that's kind of the same as saying not collinear. So 3 points in a plane or 1 point in the plane, obviously, hopefully. And 2 vectors that are parallel to the plane. Again, those 2 vectors cannot be collinear to each other. Vectors don't exist in a position, so you wouldn't talk about the vector being collinear with the point or anything like that. That doesn't make sense. But the vectors can't be collinear to each other. Vectors and lines are different. So we're talking vectors here, and that's going to be what's useful to us. If you were reading about this, it would also talk about like 2 lines without a point can define a plane. Even 2 parallel lines can define a plane. But that's lines, not vectors. So that's different. Lines have points on them. So if you have 2 lines, you have infinite number of points, right? And if you have 2 lines, even if they're parallel, you have 3 points that are not collinear. So like that's different. So lines are different from vectors. These are the ones that we're going to use. Make sense? At least sort of. All right, what are the kinds of things that we can do with equations of planes and planes in general? Again, we're just going to go kind of back through a lot of the stuff that we've done with lines. Is the point on the line? Find the equation of the line. Turn the equation into this form of an equation. Those kinds of things. Find the intercepts of this plane. Planes have intercepts as well. So we're going to do all those kinds of things. And like I said, part of this is just getting used to the notation, but also getting used to the different forms and just thinking about planes. So we are given a scalar equation of a plane. How do I know this is an equation of a plane? This is what's supposed to be easy. It might not be yet, but moving forward, it's a very strict, clear, explicit detail that makes this an equation of a plane and not that of a line. The z. And I've told you there's no scalar equation of a line. So if this is scalar, which we can tell it's like in standard form, it is scalar, and it has a z part, it's in 3 space, which means it's a plane. Okay? How am I going to check and see if if both of those 2 points are in the plane? What do you think? Turns out scalar form is actually really useful when talking about planes. A lot of the little piddly things we do, we want scalar for. But then we want vector for some other things, parametric for some other things, and that's part of what you really need to know by the end of the unit is like, oh, I'm doing this, I need it in this form. Oh, I'm doing that, I need it in that form. What do you think we're going to do? Summer, do you think you know?
Substitute the points in the...
Yeah, left side, right side check, right? So for A, the left side is x plus 3y minus 2z minus 10, which is 1 plus 3 times 3 minus 2 times 0 minus 10. So that's 10 minus 10, which is 0, which equals the right side. Therefore, A is in the plane. And then for B, two minus 9 minus 8 minus 10 works out to negative 25. So B is not in the plane. Easy enough, right? I mean, again, this stuff all seems simple, but it's when we mix it all together and ask all these different kinds of things and getting used to the thinking and the notation that is challenging. And we're going to do some harder stuff in this unit. We are. Good? What about a vector equation of a plane? What do you think that's going to look like? Planes only exist in 3 space. Vector equations look like this. But what's the rest of it going to be like? Any wild guesses? I'll give you a hint. What defines a plane? A point and 2 vectors. Zach, got an idea?
So like first point, so X, Y.
Yeah, like a position vector to the point, just like, yep, good.
And then the direction vector with T and then point and then plus another direction.
You got it. So a position vector P, we actually use S as a standard times direction vector 1 plus T times direction vector 2. I think this is obvious, but it would, a general example. If direction vector 1 and direction vector 2, and they're not direction vectors in the same way that they are for a line, because planes don't have a direction in that same sense. We still use D. I still refer to them as direction vectors, but they're vectors that are parallel to the plane. If they were collinear to each other, you'd still be in a line. You wouldn't get the other parts of the plane. You need one direction vector to go this way and the other one to go that way to be able to get off that line. But then using that, you can get anywhere on the plane. Is a position vector to a point on the plane, and direction vector 1 and direction vector 2 are, like we said before, vectors parallel to the plane and not each other. Any question? Okay, let's do some different things with planes. Find the vector and parametric equations for each plane. This one's straightforward. It just gives us two vectors. I mean, you can assume that A and B are vectors that are parallel to the plane. And it gives us a point. So we just go ahead and write it. Position vector will come from the point. Position vector to a point in the plane. So that's 0, 1, 5. And parametric is very straightforward. The fact that it's got x, y, and z in parametric form just has to do with 3 space. So that's not telling me that it's a plane. what will tell me that it's a plane? So this is 0 plus 5s minus 2t. The fact that it's got s and t in the parametric form, it has to be a plane. So this is what I'm saying. If you got to the test and you looked at this and thought it was a line, or vice versa, looked at a line and thought it was a plane, I mean, things are going to go really badly. Okay? But it's straightforward which one's which. Okay, and y will be 1 minus 3s plus 5t, and z will be 5 plus 0s plus 7t. And we might refer to this as like pi 1 or something, but you could call it p as well. Okay, so that was pretty easy. We were just given the items that we needed. This one's a little bit, got a little bit more to it, I guess. So we're going to write the equations of a plane that contains this point, and it's parallel to these two lines. What does that mean, parallel to those two lines? How is that going to help me come up with the equation of the plane?
Well, the parallel to the first one, like one a vector would just be goes across. You have to use it.
What would have to? What part of it? Yeah, you're right, but what part of it would?
I want to say like the 5 to 11.
Okay, you're on the right track, but that's not going to work. This is a position. What is this, first of all? So this is what I mean. We should be able to look at that, maybe not yet, but soon, quickly, and know what that is. It's a line. How do you know it's a line? It's only got one direction vector and a position vector. Direction vector has a scalar in front of it. So this is a direction vector of this line. Good? Okay, so how do I find the equation of the plane? What do we need to find the equation of a plane? 3 points. Do we have 3 points? I'm going to answer that one. We don't. These position vectors to these points are not necessarily on the plane. It doesn't say that. It says parallel to the line. It doesn't say the line is in the plane. So this point won't help. This point won't help. Or those position vectors. How could we do that? It's asking us to find the vector equation. That's what the instructions said. Find a vector and parametric equations. We could find the scalar equation. We could also find the vector equation. Zach, what do you think?
Do that too first. Point like P as a position vector, and then use S as one direction vector, and then T as another.
We need a point and two direction vectors. If it's parallel to both of these, can't I use those two direction vectors as the ones I need for the plane? Exactly, very good. So my position vector is going to be 4, 0, negative 6. My first direction vector can be negative 1, 5, 4. My second one can be 9, negative 2, negative 3. Okay, you shouldn't need my help to do this, so go ahead and write those. Not sure if I mentioned this. I think it's worth stating. S and T are different, right? The scalar for one and the scalar for the other are different. You can't use T and T. That wouldn't work. So S and T are different variables because they have to be able to be different values to get to every point on the plane. Okay, and then again, X is going to be 4 plus 5s minus 2t. Y is 0 plus 5s. Whoops, that should be 9t. Get ahead of myself here. Oh, yeah, I did all that wrong. Minus s plus 9t. Sorry, I was looking at the y's. Plus 5s minus 2t. And then z, 6 plus 4s minus 3t. Okay. Good enough? Ooh, this is a good one. Can we find the equation of a plane with the following intercepts? X-intercept, Y-intercept, Z-intercept. What does this even mean? What does it mean if I have an x-intercept of 2? Yeah, good. So we have 3 points that are linearly independent. I think we're going to see that. So that defines a plane, and we will be able to come up with the equation of the plane. If I have an x-intercept of 2, what does that mean about that point? Y is 0. What else? Z is also 0. Very good. Both of the other coordinates are 0, so that's important to note. So it's on the x-axis. So if this is point P2, 0, 0, y-intercept is 3. I'll call that Q, 0, 3, 0. And then call that one R, 0, 0, 4. Defines a plane. The plane is not triangular shaped. But that triangle is in the plane, but the plane goes off forever in every direction. Just because I drew a triangle between those 3 points doesn't mean the plane is a triangle. No more than when you plot 2 points in 2 space and connect the line. Back in grade 9, a lot of people just connected the dots and the line stopped at the dot, which is a line segment. But you finally learn to draw a line through those dots that goes off with arrows in both directions. So plane is the same way. Planes are harder to draw, though. So turning this into some kind of bigger plane would be tricky. So how am I going to find the equation of this thing, though? If I want to find a vector equation, I still need the same parts that we've been using. Yeah, very good. I can find direction vectors between these points. Remember what I said in the last unit? You're going to be doing a lot of this. Can you find a vector between PQ, between PR, between QR? And yes, we can. And we have 3 points, so we can pick whichever one we want to be the position vector. So I'll choose P. And I will choose PR for my first one. And what's the trick here? Subtract backwards. Because these happen to be intercepts, this happens to be really easy. So it's 0 minus 2, 0 minus 0, and 4 minus 0. And 0 minus 2, 3 minus 0, 0 minus 0. Happen to just be a lot of zeros because these are intercepts. You could be given any 3 points, and then you may or may not have zeros like that. And I'm only going to write the parametric equations again because with all the zeros, it sort of shows how these things can simplify. And sometimes you're given a parametric equation, and it might look strange, but like that shouldn't be a stumbling block for us, I don't think. So x will be 2 minus 2s minus 2t, but y is 0 plus 0s plus 3t, so just 3t. And z is 0 plus 4s plus 0, so just 4s. Good enough? Questions, questions, questions? Summer, you look a little unconvinced about something. You okay? Okay, find the scalar equation of the plane in part C. How in the world are we going to do this? I said before, a lot of the little piddly things that we do, scalar form is very useful. And part of what you have to get used to both with lines and with planes is what form is good for what. And then be able to turn it into that form if you don't have that form, and then use it to do whatever you're being asked to do. Okay? Just like equations of lines. Sometimes we want y equals mx plus b. Sometimes maybe we want a different version. How am I going to do this? Any ideas?
We have a direction vector, so we can find the normal vector from it.
Aha. How are we going to do that? And why is the normal vector going to be useful?
Because the normal vector can be found from the scalar equation.
Because the normal vector is in scalar. Very good. So, how am I going to find the normal?
One of the direction vectors dot product between normal and zero.
It will. But in 3 space, if I only have one direction vector, if I find something that's orthogonal to that, so dot product is 0, that could be anywhere. So my plane might be like this. So if I just take one direction vector and find something that's orthogonal, that may not be normal to the plane. So there's a little bit more to it. What do we need? So the dot product's not going to help. What might help? What other tool do we have? Cross them as in the 2 direction vectors, because then I'm going to get a vector that's orthogonal to both direction vectors, which has to be normal to the plane. So that's what we do. Very good. So we're going to find n, which is equal to direction vector 1 crossed with direction vector 2. So a reminder of how to do this: 0, 4, negative 2, 0 with 3, 0, negative 2, 3. 0 minus 12, negative 8 minus 0, and negative 6 minus 0. In other words, if I just think about the dot product, I'm going to get something that's orthogonal to one of the direction vectors, but not necessarily, and probably not, the other direction vector. Okay, so that won't help us. And I'm going to show you a little trick. We're actually, when we do this, we're not actually finding n. I mean, we are in a way, but we're going to call it kn. And we're going to say this is kn. That way, the normal that we choose can be a reduced version of this. So I'm going to divide everything by negative 2. Smaller numbers, reduced, we're all working with the same values. They're all good positives to doing this. I want you to show it this way. I want you to do this. First find kn so you can reduce it. You can't say n equals this, and then equals something else different. So we have to call these kn so that we can reduce it. And I want you to use the reduced version. Okay, so what does this mean? Those are the coefficients of my scalar equation. So it's 6x plus 4y plus 3z. What comes next? What's the constant, Seema? No, not necessarily. Not necessarily. Good idea, because it is in other, like in y equals mx plus b, but not in standard form, not in the scalar equation. We don't know what it is. We don't know what the constant is. So we're going to have to call it d. But that's not very useful. So now what do we do? Sub one of the points, pick your favorite. What do we have? 2, 0, 0. Solve for d, restate the equation. So it looks, in this case, like d is negative 12. And that's it. We were asked to find the scalar equation, so we're done. This process is useful because, like I said, a lot of the little things we do, we want scalar equation for. It turns out it's actually useful for a lot of little things. Cross product of the two direction vectors if you're in vector form. Get your normal simplified. Come up with the general form with a d, plug in a value, solve for d, restate your equation. Any questions? Okay, we're going to do a couple more just general kinds of questions. This is supposed to say find the intercepts. A plane could be parallel to one or two of the axes. So it may not have 3 intercepts, but it might. We already saw one that does. Again, that's something you should spend some time visualizing and thinking about, I think. But I think this one will have all 3. So, how do I do this? But how am I going to do that? Can I do that? Like, do you know how to do that? Because I like that idea. That's how we would have done it in 2-space. Sub 0 in for y and solve for x. But we would have to be guessing at what s and t are. Scalar form. Remember I said that it's useful for a lot of little things. Good idea. If it's in scalar form, I can sub in 0 for y and z or x and z or whatever and solve for the remaining part. You agree? Okay, good job. So scalar form. How are we going to do that? Dot product of the direction vectors. Negative 18 minus 0. 20 minus 12. And 0 minus negative 12. You don't have to switch the signs there, but you might want to, you could. Plus d, some people forget the plus d part, and they either make up a d from here somewhere, or they just leave it like d is 0, but it's not. So Be mindful of that. How do we solve for D? Bradley? What point? Yeah, so this is a position vector to the point 1, 2, 3 that's on that plane, because that's the whole point of vector form. So we've got that 1 point. So let's use it. Good. And I think this works out to 17. And instead of actually subbing in all the zeros and solving, I think we can just, by inspection, pick out the intercepts here if this is something you were asked to do. So if the x-intercept will be when y and z are 0, I move the 17 over, it becomes negative, divide by 9, so this should be negative 17 over 9. This will be negative 17 over negative 4. And this will be negative 17 over negative 6. Is that okay? Okay, and finally, determine if this point is in the plane. How are we going to do this one? Any thoughts? Scalar form again. It's always scalar form, it seems to be. And then what are we going to do? We already did that. Left side, right side check. Very good. So put it in scalar form. But you see what I mean? It doesn't say, part A, put the equation in scalar form. Part B, use scalar form to, like, you got to know that this is what you do, right? But scalar form. So go ahead and try that one on your own. I'll do it too. But try not to just copy me. See if you can do it yourself. To solve for D, we need a point. What point should I use? Should you use? Why not point P? Huh? Yeah, we're checking if that's in it, but I could see somebody not thinking carefully and using P here and then checking P and like, oh yeah, it's in the plane. Well, of course it's in the plane. You use that point to define the plane. This, the position vector to this point, 2, 5, negative 3, we know is in the plane. So you got to use that one. (28) plus 20 plus 3 is 51, so D is negative 51. And now I'm going to check the other point. That's 56, yeah? I don't know. Should I not? Oh, because this is -1. So I just chose to flip the signs. You wouldn't have had to. You know, 1 negative is a bit easier than 2, maybe. I don't know. But like, this used to be a thing where like we always made the x coefficient positive in grade 9. That's sort of a recommendation. It's not a rule, but it's sort of recommended. So sticking with that kind of norm, I suppose. This looks like 56 minus 4 minus 1 minus 51, so that's 0. So P is in the plane.